Hello everyone. This video is titled Solve Uniform Motion Applications. All of the exercises I'm going to do in this video are taken directly from a free online textbook at openstax.org, and I'm in their Intermediate Algebra 2nd edition text. I'm in section 7.5 titled Solve Applications with Rational Equations. And as I said, the title of the video is Solve Uniform Motion Applications. So word problems involving, the distance and speed and time that people are traveling for. And whenever, when they say uniform motion, that just means that, you're traveling at a constant speed, right? The same speed. The exercises I'll be working on are numbers 285 all the way to 304. All right, so that should be 20 examples. Each example corresponds to a different number, right? So in the video, example 1 will correspond to number 285. Example 2 will correspond to number 286, all the way until example 20, which will correspond to number 304. So, and I will also have time stamps for each example. So that way, if you want to look at a specific one, you just count down to which example it is and click on that timestamp in the video description. Okay, and then one request I have of you is that when I start a new question, pause the video and try to work on it yourself first. All right, then watch me do it and compare your work with mine and see if how you're grasping the material. Because if you're just watching me work on it and not practicing yourself, you're probably not learning much of anything. All right. So every single one of these exercises is just it's just solve the application problem provided, and they're all related to some sort of uniform motion. All right. So example 1, exercise 285. We have Mary. Mary takes a sightseeing tour on a helicopter that can fly 450 miles against a 35-mile-per-hour headwind. In the same amount of time, it can travel 702 miles with the 35-mile-an-hour tailwind. Find the speed of the helicopter, right, without the wind, right? So against the wind means that this 35-mile-an-hour headwind is decreasing the speed of the helicopter by 35 miles per hour. Traveling with the wind means that the speed of the helicopter is being increased by 35 miles per hour. We're going to be assuming that. Okay, so I'll keep this problem up. Alright, so you can see 285 still up top. I got some paper here. Now, in all these uniform motion problems, hopefully you can see my writing, and I will bring the paper up bigger in a little bit. Alright, but in all the uniform motion problems, we're going to be making use of the following facts, right? The following concept, the following formula. That the distance traveled is equal to the rate of travel, or speed. You might also refer to this as speed, but very often they call it the rate of travel, miles per hour, meters per second, whatever, multiplied by the time traveled for. And hopefully this makes sense. If you travel 30 miles per hour for 4 hours, well, 30 times 4, that's 120 miles you have traveled, the distance, right? Now I will be abbreviating this as d equals r times t. Right? Distance equals rate times time. Now we are in a section here of this textbook that deals with rational equations, fractions showing up. So not only will this concept come into play, d equals rt, but we might also have to solve for r or solve for t here. If I solve for r, we would just divide both sides by t. We'd have r equals d divided by t, right? A fraction. So the rate, the speed, equals the distance traveled divided by the time traveled for. Right? And again, hopefully that makes sense. If I go 100 miles in 2 hours, 100 divided by 2, that would be 50 miles per hour. That would be your rate. Or we might have to solve for t. And if d equals r times t, then t would be equal to the distance divided by r, right? The distance divided by the rate, d divided by r. So any one of these, right, any one of these is a valid formula. And we're going to be using one of these relationships in all of these problems. All right. So let's keep that in mind. All right, so what I like to do for uniform motion problems, distance, rate, time problems, I like to make a little table. I like to make a table where we have a distance column, a rate column or speed column, and a time column. All right, and we actually make these into columns here. And for all these distance, rate, time problems we're going to come across, there will most likely be 2 trips or 2 types of travel that are discussed. So I'm going to make this into a 3-column and 2 rows table, and each row will represent the different type of travel. So we have the helicopter traveling with the wind and against the wind, right? We have the trip against the wind, against the headwind. And we also have the traveling with the wind, right? They describe 2 different trips, 2 different ways of traveling, which will be in each row. Sorry, with, not wind the wind, with the wind, with that tailwind. And I'll start filling in the information in this table. But so I read through this, and and I read through the question, and just like any other word problem, you read through the question carefully, right? Make sure you understand what's happening, which is sometimes difficult. Then you ask yourself, what is it they want from me? What don't I know? And you assign variables, you assign expressions to those unknowns. Now look at the very end. Usually in a math textbook, that'll be stated at the very end of the question. See, it's find the speed of the helicopter. So I'm going to let the speed of the helicopter I'm going to call this S for speed. And this will be in miles per hour, right? Because I'm noticing that the winds, right, when they mentioned the headwind and the tailwind, those speeds are in mph, right, miles per hour. All right, and then something else I like to do in my table is above the distance column, I'll write the units. Right, the distances should be in miles. The rates column, that'll be in miles per hour. Right, that's a rate, miles per hour, mph. And the time column here, time's going to be in hours, right? Yeah, I like to write the units. You don't have to do that. All right, so now that I have a variable representing what they want from me, right, the speed of this helicopter, without the wind, right, let's go through and start filling out the information in this table. So, reading through it again, right, Mary takes a sightseeing tour on a helicopter that can fly 450 miles against a 35-mile-an-hour headwind. So the distance traveled against the wind, they're saying, is 450 miles, right? I don't have to write the word miles here because I already say that, the distances are in miles. Against a 35-mile-an-hour headwind. So remember I mentioned earlier these with the wind, against the wind problems. We're going to just very, very much simplify this. So when they say the helicopter is traveling against a 35-mile-an-hour headwind, its rate of speed would be the speed of the helicopter, right, which again I called S, and then going against the wind slows that speed down by the speed of the wind, right? So minus the 35-mile-per-hour headwind. So I hope this makes sense, that the rate that the helicopter is traveling at would be the speed of the helicopter, minus that wind speed. Because again, we're going against the wind, it's slowing us down. And now that I have two of these, once you have two of these filled in a row, you should be able to figure out the third box using one of these relationships I wrote up here. Distance equals rate times time, or rate equals distance divided by time, or time. And here it is, we're filling in the time box, and time is distance divided by rate. So in the time box here, I take the distance, 450 miles, divided by the rate, this s minus 35. All right, so that's all against the wind. Right. Then they say that this can fly 450 miles against a 35-mile-per-hour headwind in the same amount of time. Right, so that's going to come into play when we write an equation. We eventually are going to write some sort of rational equation to solve. It can travel 702 miles with a 35-mile-per-hour tailwind. So this is with the wind. So it can travel, 702 miles with the wind, and then that's, with a 35-mile-per-hour tailwind. Now with the wind, you have the speed of the helicopter, and then added to that, we get 35 miles an hour faster with the wind, right? So the rate of the speed of the helicopter is, speed of the helicopter with the wind plus 35. And then once again, once two of these boxes are filled in a row, you can find the third one using those two. The time, again, is distance divided by rate. So 702 divided by the s plus 35. All right, next comes the equation. All right, I want to set up some sort of equation with all this information, and it's going to be a rational equation. And you should be able to solve rational equations based on our work in section 7.4 of this same text. Well, reading back through it one more time, it says, and I'll kind of reword it myself here to make the equation hopefully easier to see, and I think this is probably the hardest part for most students, is being able to use the information to set up a proper equation. Because after you set up the equation correctly, the rest should be simple, solve and check. But setting up the equation is, I feel, the hardest part. Well, the key words here are, it makes this trip, it flies in this trip against the wind in the same amount of time as it makes this trip with the wind. So the time traveled, I'll write this in words here. Now, I'll make this bigger now. So time traveled against the wind is the same, right? It was the same amount of time, it said, as the time traveled with the wind. Right. So that leads me to this equation here. I look at my chart, my table, and the time traveled against the wind was this expression, the 450 divided by s minus 35. And this is the same as, right? The same amount of time, so is equal to the time traveled with the wind, which is this expression in my table, the 702 divided by s plus 35. Right, and then we're solving this equation. And of course, check your solutions and also make sure at the end that your solution makes sense with the problem being discussed, right? That it makes sense in real life. All right, so rational equation here. Find the LCD. All right, now hopefully it's obvious here. There's only these two denominators. They're already factored. The LCD is just s minus 35 times s plus 35. And I multiply both sides by this LCD, right, the least common denominator, and that should cancel all the denominators, right, make it a lot simpler to do. So left side I have 450 divided by s minus 35, and this is getting multiplied by the LCD. So times this, s minus 35 times s plus 35. And same thing on the other side. And we have 702 divided by s plus 35. And this is also getting multiplied, right, by the LCD, s minus 35 times s plus 35, right? Again, I said earlier, the whole reason you multiply both sides by the least common denominator is to get rid of all the denominators. On the left side, the s minus 35s would cancel, and I'm left with 450 times the quantity s plus 35, right, because that's the only factor remaining from the LCD. All right, equals, then on the right side, the s plus 35s would cancel, and I have 702 times the only factor left from the LCD, this quantity s minus 35. Alright, now I'm going to pull out a calculator. This is just off to the side. I don't need to take up your screen with it, but distributing the 450 on the left, we'd have 450 times s plus, and then 450 times 35 would be 15,750. Alright, that's 450 times 35 equals, and then over here distributing the 702, I have 702 times s minus, and then 702 times 35, so minus 24,570, and then I would subtract 702s, give me negative, right, 450 minus 702 be negative 252, right? So I have negative 252s on the left, and then subtracting 15,750, So we got, negative 24,570 minus 15,750. Go over here, negative 40,320. And then we're dividing by negative 252. And that'll be a positive value, right? Negative divided by negative. And again, I'm just doing a calculator work off to the side here. You can use whatever calculator you wish, I don't care. All right. And this is equal to 160. Now, as with most word problems, applications, sure, you solve the equation, great, but go back, what did this represent, right? What did S represent? S represented the speed of the helicopter in miles per hour. So then usually you should be writing your answers in complete sentences, right? They asked us to find the speed of the helicopter, and I'm just going to write off to the side here, the speed of the helicopter is, in this case, 160. And again, units should be on these numbers to give them meaning, right? Miles per hour. It represented the speed of the helicopter in miles per hour. Right. Wonderful. And then you can even go back and check in the chart here, just replace S with 160 and see, is the distance equal to the rate times the time that you get, and do it for both rows, and it should be good, right? You should, if I did, and I know I did everything correctly here, but check it out yourself. Go back to your table, replace all the S's with 160, and see if the distance is in fact equal to the rate times the time. All right. Wonderful. All right, so that was example 1, exercise 285, and pretty much the rest of them I'm going to set up in a very similar fashion with these tables, these 2-row tables, distance, rate, time tables. All right, so example 2 is going to be exercise 286. Scroll this down a tad. All right. So this reads, a private jet can fly, and this is very similar to the previous problem. You have a flight against the wind and a flight with the wind. So a private jet can fly 1,210 miles against a 25 mile per hour headwind. In the same amount of time, it can fly 1,694 miles with a 25 mile per hour headwind, tailwind. Find the speed of the jet. All right, so once again, I'll keep the problem up here and you can see it, and I'll make another table. All right, distance, and this will be again in miles, the rate in miles per hour, the time in hours, these 3 columns, and then I'm going to have 2 rows, 2 rows, 1 row for each trip. And once again, we have the trip that this jet takes against the wind, and the other trip this jet is taking is with the wind. Now the trip against the wind, and oh yeah, one more time here too, right? Just like any word problem, I'm gonna use the letter J to represent the speed of the jet that they asked me to find, right? The speed of the jet without any wind. So I'm going to use J. You could use S again if you want, it doesn't matter, or X, whatever you want. Just using J for jet. So the trip against the wind, right? They said the jet can fly 1,210 miles. That's the distance traveled against a 25 mile per hour headwind. So the rate of speed would be the speed of the jet, right, J, but then minus 25, right? We're against the wind. That's 25 miles an hour, so minus 25. And then as before, as in the previous example, the time is the distance divided by the rate. So 1,210 divided by J minus 25. Okay. Then with the wind, it said it'll fly 1,694 miles with the wind, and that tailwind is 25 miles per hour as well. So the rate of speed with the wind is, the speed of the jet plus 25. The wind's making it faster. And once again, the time is the distance divided by the rate. So 1,694 divided by J plus 25 here. And I won't write this one this time, but let's make this bigger. It did say again that the time against the wind, the time it took to travel 1,210 miles against the wind, was the same amount of time it took to travel 1,694 with the wind. Right? So once again, the times are equal. So the time to travel against the wind was 1,210 divided by J minus 25. That should be the same amount of time, right, equal to the time traveled with the wind, 1,694 divided by J plus 25. And I'm solving this for J and then answering their question. Now the LCD, I hope you see it's obvious again here. The least common denominator is J minus 25 times J plus 25, and instead of actually writing it on both sides, I'm just going to do this. I'm going to say you're going to multiply that fraction on the left and the fraction on the right by the LCD. And the whole reason for doing that is to cancel some factors, right? Cancel the denominators. On the left side, right, the J minus 25s would cancel. And I'd have 1210 times J plus 25. Equals, and then on the right side, the J plus 25s would cancel, leaving me with 1694 and J minus 25. Okay, and then I have a calculator, off to the side. I'm just gonna, again, use whatever you want. Distributing the 1210 here, we'd have 1,210 times J plus, let's see, 3250, let's see, 1210 times 25. 30,250. 30,250. Then on the other side, again distributing the 1694, we have 1,694 times J minus, and then 1694 times 25 is 42,350. Alright. I'm going to take, I'll just do this here. We got subtract the 1694J, 1210 minus 1694. So that's negative 484J on the left side. And on the right side, subtract 30,250. That'd be negative 72,600. And then we divide. So I'm going to pull this up here. I don't feel like bringing up a new piece of paper. And we'll have J equals, so dividing by 484 here. So 72,600 divided by 484 is a nice 150. Now again, this is great and everything, right? This is the solution, and you can, and please double check it, right? Replace J with 150 and see that all this stuff makes sense. Everything's true. The distance equals rate times time for each trip. But then what we should be saying though is the jet is traveling, or the speed of the jet is 150 miles per hour, right? All these speeds were in miles per hour. I'll just put mph again. Right? But yeah, like with any application, right? You should give the numbers should have units on them to give the meaning. You should be answering in complete sentences, right? And making sure it makes sense, right, with the problem. Great. So yeah, very, very similar question, that one, to number 1. All right, so next question, next example, the exercise 287. All right, so this is very similar, but instead of wind speed, we have the speed of a stream, the speed of water. So exercise 287 reads, a boat travels 140 miles downstream. Now, downstream means with the current, with the water. The water is speeding the boat up. In the same time as it travels 92 miles upstream. Upstream means you're going against the current, against the water. Right? And the speed of the current, right, the water, is 6 miles per hour. What is the speed of the boat? So this is, again, very, very similar to the first two questions. Right, so once again, I'm going to make the same chart. So example 3, right, this exercise 287. And I'll make a distance in miles. The rates are again in miles per hour. And the times are again in hours. 3 columns. And I'm going to make 2 rows. One going downstream, right? The boat going with the water, with the current. And then the other trip upstream, which is against the current. And they're asking me to find the speed of the boat. I'll use the letter B to represent the speed of the boat, which will be in miles per hour, right? All the rates here are given to me in miles per hour. I'm just using B for boat. Right? You can use whatever you want. Okay, the trip downstream. So the boat travels 140 miles downstream. And the rate of speed going downstream. Now again, downstream means you have the boat speed and then you're adding the speed of the current, right? You're going with the current, so B plus the 6 miles per hour that the current is traveling. And then once again we have time is distance divided by rate. So 140 divided by B plus 6. Right, then the trip upstream against the current, traveling 92 miles upstream. So remember, this is against the water's slowing you down, so you have the speed of the boat minus the 6 mile per hour current. Right, you're getting slowed down by 6 miles per hour. And once again, the time is distance divided by rate, so 92 divided by B minus 6. Right, and then just as in the first two questions, they have, in the same time, right, in the same time. Okay, so I'll make this bigger and we're going to just equate the times, just like the first two questions. So the time it takes for this boat to travel 140 miles downstream, which is 140 divided by B plus 6, is the same as, right, equals the time it takes to travel 92 miles upstream. So 92 divided by b minus 6. Alright, so once again we find the LCD. Alright, now the LCD is again obvious here. It's just b plus 6 times b minus 6. And I multiply both the left side and right side fractions by the LCD, and they'll cancel all these denominators. Left side b plus 6 would cancel. I'd be left with 140 times the quantity b minus 6. Alright, on the right side, the b minus 6's would cancel, and I'd be left with 92 times, and then the only factor left over from the LCD is the quantity b plus 6. Alright, distributing the 140 over here, we have 140b minus, and 6 times 14, that's 60 plus 24, that's 84, so this is 840, you add a 0 there. And then over here, distributing the 92, we have 92b plus, and then 552, right? 540 plus 12, 552. 6 times 92. Then subtracting 92b would be give me 48b on the left side, and adding 840 gives me 1,392 on the right side. And then we divide by 48. Right, dividing by 48, which I know I could do this out loud, but 1392 divided by 48, it's a nice even 29. So again, this is the solution to this equation. Cool. Make sure it makes sense. I'll put a check mark, right? Check your work. Replace b with 29 back in your chart up here, and make sure that the distances are equal to the rates times the times in each row, and it should work out. And then what I'll say is that the speed of the boat, or the boat was traveling at, the speed of the boat in this scenario is 29, and once again the units on that are miles per hour. Great. Okay. So next example. You're gonna get bored of this stuff. Number 288. Very similar. Another. This is one with wind again. So this is example 4. This is very similar to examples 1 and 2. Darren can skateboard 2 miles against a 4 mile per hour wind in the same amount of time he skateboards 6 miles with a 4 mile per hour wind. And find the speed Darren skateboards with no wind. Right, so the speed of Darren's skateboarding without wind. So this is once again. I'll pull this up. Leave the question up. Number 288 on top there. So once again, example 4, making the same table. Distance. Now they mentioned miles and hours again, so this is distance in miles. The rate is in miles per hour. The times are in hours. 3 columns yet again. 2 rows, right? One against the wind, right? Him skateboarding that, making a trip against the wind. And the other one making a trip with the wind, skateboarding with the wind. And I'm going to let, I already have a D up there. I'll let X this time, why not? It doesn't matter, like I said, it doesn't matter. As long as you don't use the same letter for multiple things. I'm just going to let X be Darren's skateboarding speed with no wind. So the trip against the wind is described, right? So Darren can skateboard 2 miles against a 4 mile per hour wind. So his rate of speed would be, the speed he would go without the wind, which I called x, but then minus the wind speed, right? Minus 4, right? The wind speed slowing you down. You're going against it. And then once again, time is distance divided by rate. 2 divided by x minus 4. That's how long it would take him to take that trip. All right, then with the wind, he would skate in the same amount of time there. He skateboards, 6 miles with the wind, which is also 4 miles per hour, the wind. So his rate of speed with the wind is, his speed without the wind, and then with the wind you're adding the speed of the wind, right, making you faster, x plus 4. Time, distance divided by rate, 6 divided by x plus 4. And once again, it says that these two trips are taken in the same amount of time, right? The time he skateboards 2 miles against the wind is the same amount of time as he skates 6 miles with the wind. So I'm just equating these times again. So we have 2 over x minus 4 equals 6 over x plus 4. The LCD is once again obvious, just the product of the denominators, right? X minus 4 times x plus 4. And I'm going to multiply both sides by this LCD, right, to cancel denominators. And let me make this a little bigger. On the left side, the x minus 4s would cancel. And I'd have 2 times the quantity x plus 4 equals, on the right side we'd have 6 times the quantity x minus 4, right, because the x plus 4s would cancel. Alright, distributing the 2, distributing the 6, we have 2x plus 8 on the left equals 6x minus 24 on the right. Subtracting 6x gives me negative 4x on the left. Subtracting 8 would give me negative 32 on the right. And then dividing by negative 4 would give me x equals positive 8. And don't forget to check that back in our chart, or back in the equation. So Darren skateboards 8 miles an hour. 8 miles per hour with no wind. Great. Just remember what x represented, right? Darren's skateboarding speed without the wind. Wonderful. Alright, so the first 4 questions have all been pretty much the same. But it looks like the next one's going to start differing a bit. Let's take a look. This is exercise 289, right, example 5. So here we have Jane spent 2 hours exploring a mountain with a dirt bike. First, she rode 40 miles uphill. After she reached the peak, she rode for 12 miles along the summit. While going uphill, she went 5 miles per hour slower than when she was on the summit. What was her rate along the summit? Right? How fast was she biking when she was at the summit? So again, I have 2 trips described here. The trip uphill and then her trip on the summit, right, along the summit. So once again, I'm going to make a little chart, right, a table. This is example 5. So distance, yet again, I'm seeing miles mentioned here. Rate, once again, I'm seeing miles per hour is mentioned as speeds, rates, and times again in hours. You're going to get tired of seeing me do this. Alright, 3 columns, and then again the 2 trips, 2 different types of traveling. We have her uphill trip, right, her trip uphill, and then her trip along the summit. And they want us to find her rate along the summit. And her name's Jane, so I'm going to say J for Jane. Let J be Jane's speed, Jane's rate along the summit. All right. So that's here. I'm just going to put J right there right now. That her rate of travel along the summit I'm calling J. And another thing that was mentioned was she went 5 miles per hour slower when she was on the summit. Oh, sorry, I read that wrong. It says while going uphill, she went 5 miles per hour slower than when she was on the summit. So the uphill rate needs to be 5 less than the summit rate. And if the summit rate is J, what's 5 less than J? That would be J minus 5, right? So her rate, her speed along the summit, or her speed uphill, sorry, is the speed of on the summit that she's traveling for minus 5, right? She's going 5 miles per hour slower going uphill. Okay. Now, earlier on it says she rode 40 miles uphill. So in the uphill distance, 40 miles. And then after she reached the peak, she rode for 12 miles along the summit. So the traveling along the summit was for 12 miles. We got 40 there, 12 there. And then once again, we're saying that time is distance divided by rate. So the time traveled uphill would be 40 divided by J minus 5. The time traveled along the summit is 12 divided by J. Alright, now here's where it gets a little different. These times are not equal. In the first 4 questions, we were setting the times equal to each other. This is different. Look at the very beginning of this. It just says Jane spent 2 hours exploring a mountain with a dirt bike. So the time going uphill, and I'll put this in, I'll make this bigger now. Okay, so the time going uphill and the time going along the summit make a total of 2 hours. Right, because again, that first sentence was Jane spent 2 hours exploring a mountain with a dirt bike. So now these times aren't equal. It's these times put together make 2 hours. So here's where our equation, so the time going uphill, 40 over J minus 5, plus the time along the summit, 12 divided by J, needs to make a total equals 2 hours. So here's our equation now, right? So this is rather different than the first 4 questions. Alright, so once again, LCD should be obvious here. And this isn't a video about how to find the LCD. It would be J times J minus 5, right? J times the quantity J minus 5. And then every term on both sides gets multiplied by the LCD. Right, I'd be multiplying this fraction, this fraction as well. You'd be distributing the LCD to both these fractions on the left side. And then on the right side, you'd just be multiplying the 2 by the LCD, right? So after doing that, right, all the denominators should cancel. Now that first fraction on the left side, the J minus 5s would cancel, and I'd be left with just 40 times J. So 40J plus, right, plus second fraction, the J's would cancel, And I'd be left with 12 times j minus 5 equals, and then over here there's nothing to cancel, so it'd just be 2 times the LCD, 2 times j minus 5. So it looks like this is going to end up being a quadratic equation. And then we have to figure out, what numbers actually make sense when talking about this problem. All right, so the left side, I distribute the 12 here. We'll combine like terms. That'd be 52j, right? 40j plus 12j, minus 60, right? 5 times 12 equals, and over here I got 2j to distribute. That'd be 2j squared, 2j times j, minus 10j. And then I'll take everything to one side. So I'm going to subtract the 52j, add the 60, so I'll have 0 on one side. And 2j squared, no other j squared terms. Then negative 10j minus 52j would be negative 62j. And then adding the 60 gives me plus 60 over here. And one thing I'm noticing is that all the coefficients are even. So an easy thing to do here would be to divide by 2, divide both sides by 2, get the numbers a little smaller. And I'm going to switch sides. I personally like things on the left, right? So we have j squared minus 31j plus 30 equals 0. And this is factorable. This would factor to j minus 30 times j minus 1. Right. J minus 30 times j minus 1 would give me this. And this would only be equal to 0 if j were equal to 30 or if j were equal to 1. Now, as with other word problems you've probably seen in the past, think about what actually makes sense. Alright, so let's check these. Let me go back to my chart. Now this is about a person biking up a mountain. Think about what makes sense. If j were 1, so that'd be here. That means along the summit, she'd be biking for 1 mile an hour. 1 mile an hour along the summit. But if j were 1, do you see how the rate uphill would be negative? Right? If j were 1, the rate uphill, the speed uphill, would be negative 4. And these are speeds. Speed can't be negative. Velocity can, but we're talking about speed. It doesn't make any sense for her to be biking negative 4 miles an hour uphill. So even though this works in the equation, j equals 1 does work in this equation. You could replace j with 1 and this would be a true statement. It just doesn't make sense in real life. All right? So this works in the equation, but doesn't make sense in reality. So you got to think about that. What makes sense in the context of the problem. Right, so that's why I'm crossing out j equals 1. The only one that does make sense is j equals 30. All right, if j were 30, that means she was traveling 30 miles an hour along the summit and 25 miles an hour going uphill, and those are both valid speeds. Right? Speeds are always a positive number or a non-negative number. So Jane traveled or biked 30 miles per hour. And this was along the summit. Remember, j, I said, was her speed along the summit, which was what they were asking for. traveled 30 miles per hour along the summit. Now if they asked what was her speed going uphill, remember that was just j minus 5, that'd be 25 miles an hour. So just again, focus on the questions at hand, and they may ask you other questions, but just pay attention. Alright, so that was a little trickier because you had to do a little more thinking at the end, but still the same concept, right? You're eventually setting up some sort of rational equation here with our information. The next question, which will be example 6, exercise 290. It's about exercising. So here Lainey wanted to lose some weight, so she planned a day of exercising. So she spent a total of 2 hours riding her bike and jogging. Right? So this means that the time riding the bike along with the time jogging makes a total of 2 hours. So maybe like an hour riding a bike, hour jogging, or an hour and a half riding the bike and half an hour jogging, right? The times together make 2 hours, and that's where our equation is going to come from. We're going to have the time riding plus the time jogging equals 2. Alright, so she biked for 12 miles, jogged for 6. Her rate for jogging, her speed for jogging, was 10 miles per hour less than her biking rate. What was the jogging rate? What was the jogging rate? Alright. So very, very, very similar setup to the last question. And every question here, right, these uniform motion problems, I like to put a distance, rate, time. So again, the distance in miles is example 6. Distance in miles, the rate in miles per hour, the time in hours. And the two types of travel here, the two trips being made, one is riding bike, let's put bike, and jogging. Alright. And I'm going to I'll use J again because jogging, J for jogging. This is what was her rate while jogging. So I'm going to have J be Lainey's jogging speed, jogging rate. So that'll go under the R for jog, J. And it did say that her rate jogging was 10 miles an hour less than the biking rate. Another way to say that would be that the biking rate is 10 miles an hour more. So the biking rate would be J plus 10. I hope that makes sense, right? Because J plus 10, you go 10 less than that, you're back at J, right? And they did say that whatever the jogging rate is has to be 10 less than the biking rate, or the biking rate has to be 10 more than the jogging rate is another way to say that. It says she biked for 12 miles distance, jogged for 6 miles. And then just like before, just like all 5 questions so far, we're using the relationship that the time traveled is the distance divided by the rate. So time here is 12 divided by J plus 10. The jogging time would be 6 divided by J. And it also says, she spent a total of 2 hours doing these things. So like in question 5, the time biking plus the time jogging will be equal to 2 hours. So there's the equation. The time biking, 12 divided by J plus 10, plus the time jogging, 6 divided by J, equals the 2 hours. And we'll solve, this equation. Right. So again, easy enough. The LCD is just J times J plus 10. And I'm just going to write the word multiply here. we're multiplying everything by j times j plus 10. So the first term on the left, the first fraction, you'd have 12 times j, because the j plus 10s would cancel, plus the second fraction, the j's would cancel. You have 6 times the quantity, j plus 10. And on the other side, there is nothing to cancel, so you just have 2 times the LCD, 2 times j plus 10. Alright, so after distributing the 6 on the left side, got 18j plus 60 equals, on the right side, distributing the 2j, we have 2j squared plus 20j. Alright, so I hope you can see this. I'm going to divide everything by 2 and then take everything to one side here. We'd have j squared, and if I divide by 2, this would be 10j, this would be 9j, and I would subtract the 9j to make plus 1j. And then this would be 30, and I'd subtract that, and we got minus 30 equals 0. Sorry for the clutter here, but I just don't want to bring in a new piece of paper for this. And j squared plus j minus 30 factors nicely. That factors to j plus 6 times j minus 5. And this has solutions j equals negative 6 or j equals positive 5. Now, check them. Which ones actually make sense? Well, if j is negative 6, that means, she jogged negative 6 miles per hour. That makes no sense. That can't be, right? So, crossing that one out. Now, j equals 5 makes sense. She jogged 5 miles per hour and would bike 15 miles per hour then. And again, just check to see when you replace j with 5 throughout the chart that distance equals rate times time. Right. So this works. That's the only one that makes sense, in the context of this problem. And then I write the statement, they asked for what was her jogging rate, right? So Lainey jogs 5 miles per hour. 5 mph. There. Okay. Wonderful. Again, same setup every time, right? Make the same kind of table. You just have to pay attention to the key words in the problem, right? To know what kind of an equation you're setting up. And that's really, honestly, the hardest part for any question. Okay, example 7. This will be exercise 291. So it's very similar with the whole total of 4 hours doing something. So, Byron wanted to try out different watercraft. He went 62 miles downstream in a motorboat and 27 miles also downstream on a jet ski. So you have a motorboat trip and a jet ski trip. Those will be the 2 rows of my table. His speed on the jet ski was 10 miles per hour faster than in the motorboat. Bill spent a total of 4 hours on the water. What was his rate of speed in the motorboat? Okay. So again, bringing it back. Example 7. Distance, rate, time. Alright, now this time I'm going to stop writing the units because it looks like all these have miles and hours. Just reading through these, all these are miles and miles per hour and hours. So I'm just going to stop writing the units for now. And then we have the 2 trips. 2 trips. One's in a jet ski and the other's in a motorboat. And we're asked about what is his rate of speed in the motorboat. So I'm going to let M represent the speed of the motorboat. And that'll go under rate here, m. Now, it did say his speed on the jet ski was 10 miles per hour faster than the motorboat. So if the motorboat speed is m, the jet ski would be m plus 10, right? 10 miles an hour faster. Says he went 62 miles in the motorboat. 62 miles in the motorboat distance, and 27 miles in the jet ski. So 27 there. And then once again, we're using the relationship that time is distance divided by rate. So 27 divided by m plus 10. And here 62 divided by m. And at the very end it says, Bill spent a total of 4 hours on the water. So again, we're adding the times, right? The time in the jet ski plus the time in the motorboat should be 4 hours. So I'll write this equation now. 27 divided by m plus 10, right? The time on the jet ski plus the time in the motorboat, 62 divided by m, should be equal to 4. And I'll bring this equation up, make it bigger. Let's solve it. Alright, so once again, LCD is just simply m times m plus 10 here. And we're going to multiply, I'll just write the little time symbol now. And multiply everything on this equation, both sides, by this LCD to get rid of all the denominators. First fraction, we just had 27m plus the second term would be 62 times the quantity m plus 10. And then the other side would just be 4 times the LCD. 4m times m plus 10. Alright, distributing the 62 here, combining like terms, we have 27 and 62 at 89m plus 620 equals, distributing the 4m over here, we have 4m squared plus 40m. And then I'll take everything to one side, and again, I like having stuff on the left, so I'm going to put this over here. I got 4m squared, and then I would subtract 89m to get minus 49m, and then subtract 620. So I have everything on one side, 0 on the other. And then I'll try factoring this polynomial here, 4m squared minus 49m minus 620. All right. So I'm going to come back when I figure that out. I'm going to do the AC method, right? 4 times negative 620, and then try to think of factors of that add up to negative 49, and factor it by grouping and whatnot. I'll come back when I have it finished. It'll pop up on the screen. Alright, so figured it out here. We got this factors to 4m plus 31 times m minus 20. And I'll bring this here because I don't want to go to a new piece of paper. So the only solutions to this, right, you got a product equal to 0. Think about what makes each factor 0. So the first factor would be 0 when m is negative 31/4. The other factor would be 0 if m were 20. And then once again, sure, both of these make the equation true, but which ones actually make sense with the problem? If m were negative 31/4, that means that the motorboat would have a negative speed, which you can't have negative speed, and so I'm getting rid of that. The only one that makes any sense at all in reality, right, when you think about the context of the problem, is positive 20, right? If that means the motorboat was going 20 miles an hour and he was going 30 miles an hour on the jet ski. And then just double check that when you replace m with 20 throughout this chart, that the distance equals rate times time. And it should, right? Don't forget to check things. And then putting the statement to answer the question here. The motorboat went 20 miles per hour. So that's what m represented, right? The speed of the motorboat. 20 miles per hour. Great. All right, question 8. Pretty similar as well, where we're going to have the sum of two times equals a total time. All right, so example 8 will be exercise 292 here, about Nancy. Nancy took a 3-hour drive. She went 50 miles before she got caught in a storm. Then she drove 68 miles at 9 miles per hour less than she had driven when the weather was good. So what was her speed driving in the storm? Right, so we have the driving in good weather and the driving in the storm. That will make up the 2 rows of my distance, rate, time table. So once again, pulling this up, see exercise 292 on the top there, and setting up the same kind of a chart. Distance in miles, the rate in miles per hour, and the time. And the 2 rows, we have driving in good weather, and we have driving in the storm. Now the question is, or what at the end is, what was her speed driving in the storm? So I'm going to let S for storm. I'm going to let S be speed in the storm. So that'll be the rate in the storm row, S. Now it did say that she drove 9 miles per hour less in the storm than in good weather. Another way to think about that is that her speed in good weather was 9 miles per hour more. So S plus 9 is the rate for her driving in good weather. Right, as long as what you have in the storm's rate is 9 less than what you have in the good weather's rate. Alright, and says she went 50 miles before she got caught in the storm, so she was driving for 50 miles in the good weather. And then she drove 68 miles in the storm. And then the times, right? Times, again, are distance divided by rate. So the time in good weather is 50 divided by S plus 9. The time in the storm, 68 divided by S. And once again, this is like the previous 3 questions, where the times are going to add up to a total time. All right, and you see the very first sentence in exercise 292, the very first sentence is Nancy took a 3-hour drive. So the time in good weather plus the time in the storm will be equal to 3 hours. So that's the equation I'm writing. 50 divided by S plus 9 plus 68 divided by S should be equal to 3. All right, and I'll make this bigger, and we'll solve this equation just like all the others. So the LCD here is just S times S plus 9. And I'm going to multiply, right? Multiply everything on both sides by the LCD to cancel all the denominators. First term on the left would just be 50 times S, plus next term you'd have 68 times the quantity S plus 9. And then the other side would just be 3 times the LCD, 3 times S plus 9. Alright, distributing the 68 over here, and then over here distributing this 3s, we'd get the following. 50s plus 68s, that would be 118s, plus, and then 68 times 9, that'd be 540 plus 72, so 612, and 630 minus 18, yeah, 612 equals, and then over here we got 3s squared plus 27s. Alright. Okay, then I'll take everything to the right, and so, well, one thing I'm noticing is that everything is a multiple of 3. Alright. Nope, 118 is not a multiple of 3. Sorry. 118 is not a multiple of 3. Alright, so we have 3s squared. Then if I subtract 118s, that'd be negative 91s. 91 plus 27 is 118, so yeah, negative 91s. And then minus 612. And then this equals 0. And once again, I'm going to think about how to factor this, and I'll maybe I can do it now. Yeah, because I'll think about how to factor this and come back when I've got it. Alright, so it just popped up on your screen. Figured out how to factor it. Be 3s plus 17 times s minus 36. And bringing this over here. Possible solutions then are s equals, negative 17 thirds, or s equals 36. And once again, both of these numbers, they do make the equation true, but not both of them don't make sense in the problem. Because, how can her speed in the storm be negative, right? And speeds can't be negative. So I'm not taking that one. But 36 makes sense. Alright, so she's traveling for 36 miles an hour through the storm, and 9 more than that would be 45 miles an hour in good weather. But yeah, but her speed in the storm is 36 miles an hour. And again, check out, make sure that makes sense in the chart. So Nancy drove 36 miles per hour in the storm, right? That was what S represented, right? The speed in the storm. Great. Alright, so next example. I think these come in groups of 4. So you notice how the first 4 questions had a very similar setup. Questions, examples 5 through 8 had a pretty similar setup. The sum of 2 times was equal to sum total time. Let's see what the next 4 have to do. I mean, they might be the same as well. We'll see. So example 9 will be exercise 293. It reads, Chester rode his bike uphill 24 miles and then back downhill at 2 miles an hour faster than his uphill. If it took him 2 hours longer to ride uphill than downhill, what was his uphill rate? Aha. This is a little different. Alright. So again, I'll pull up make sure that you can see the problem here, exercise 293. We're making another chart. This is example 9. Another distance, rate, time chart. And the 2 rows this time, the 2 different trips, are uphill and downhill, right? Biking uphill and biking downhill. Now the question at the end is, what was his uphill rate? Right? So I'll just represent that with u. I'm going to let u be his uphill speed, uphill rate in miles per hour. So uphill rate, I'll just call it u. And then notice, when he went downhill, he was going 2 miles per hour faster than uphill. So if the uphill rate was u miles an hour, the downhill rate is u plus 2. Right. Then it says, first Chester rode his bike uphill 24 miles. So 24 miles uphill distance. And then back downhill. He rode the same distance. So 24 miles there as well. So then the times, right, the time to go uphill is 24 over u. The time to go downhill is 24 over u plus 2. Now, but these are not equal, right? And they don't give us a total time. See, what they do is give us the following. It says it took him 2 hours longer to ride uphill than downhill. It took him 2 hours longer to ride uphill than it did downhill. This is where our equation's coming from, right? So now that I've got the little wording written out there, let me pull up the page, make it bigger. So what this means is that the time downhill plus 2 would give me the time uphill. Right? Because basically the time it took to go uphill was the same as the time it took to go downhill plus 2 hours. Right? Because it was 2 hours more. So time uphill, let me write this in more words here. The time uphill will be equal to the time downhill plus 2. Right? Because again, think about it, right? If the downhill should take less time. So you take the downhill time, add 2 hours to that, and that's how long it took to go uphill. Again, I can't say it, and I'm trying to say it in different ways here, but this is our equation. So the time uphill is this 24 over u, and this should be equal to the time to go downhill, 24 over u plus 2, and then plus 2 after that. Or you could say their difference is 2 hours. Take time uphill minus time downhill equals 2. Right, same thing. But either way, we have an equation to solve now. Right. Now, once again, the LCD should be simple. Just u times u plus 2. And I'm multiplying the fraction on the left and then both of these terms on the right by the LCD. On the left, the u's would cancel. I'd have 24 times the quantity u plus 2 equals the first term on the right, the u plus 2 would cancel. I'd have 24u plus, and then the second term has no denominator, so nothing's canceling. You just have 2 times the LCD, right? 2u times u plus 2. I will bring a new piece of paper in for this. So left side, I've got 24u plus 48 equals, and over here, distributing the 2u, we'd have 2u squared plus 4u plus 24u, that'd be plus 28u. And then I'll take everything to one side and switch sides. So we have 2u squared If I subtract 24u, there'll be positive 4u over here. And I'd subtract 48, I got minus 48, and then 0 on the other side. So what I did there was subtract 24u, subtract 48, and then switch sides because I like having stuff on the left. You can keep it on the right if you want, doesn't matter. Now, one thing I noticed is that all the coefficients here are even. So just to make the numbers a little smaller, I'm going to divide everything by 2. Gives me u squared plus 2u minus 24 equals 0. This is nice and factorable, right? This would factor to u plus 6 times u minus 4 equals 0. And then so the possible solutions are u equals negative 6 or u equals positive 4. And again, think, sure, both of these work in the equation I wrote. That's fine. But which ones actually make sense with the problem? Back in the chart, back when the meanings. If you were negative 6, that means, he was riding his bike at negative 6 miles per hour going uphill. That makes no sense. You should have no negative speed, so that one I'm not counting. But the other one does make sense, right? Going uphill at 4 miles per hour and downhill at 6 miles per hour. And the time it would take him to go uphill would be 6 miles, and 4 times 6 is 24. The time it would take him to go downhill, 24 divided by 6 is 4, and then 6 times 4 is 24. In both rows, distance equals rate times time, so this checks out. All right, and then to actually answer the question, what was his uphill rate? Chester's uphill rate was 4 miles an hour, or Chester went 4 miles per hour uphill. And that's what they wanted. Okay. So my thinking is the next 3 examples will be similar to this. It seems, again, these seem to come in groups of 4. Let's see. Right, so next exercise, right, exercise 294. Scroll that up. It'll be example 10. So we're almost halfway done. Wow. Matthew jogged to his friend's house 12 miles away and then got a ride back home in a car. Right? It took him 2 hours longer to jog there than to ride back. His jogging rate was 25 miles per hour slower than the rate when he was riding in the car, I'm assuming. What was his jogging rate? Yeah, so this is again very similar to example 8. So again, example 9, very similar to example 9. So example 10. I'm sorry, I want to have the problem up there too. Exercise 294. Once again, distance, rate, time chart. On the 2 rows this time, the 2 different trips are there and back. Jogging and riding. Right, jogging and riding. And I'm going to let J be Matt's jogging speed, jogging rate. Because that's what they asked me for, right? What was his jogging rate? So I'm going to put that in the jogging row here under the rate column, J, and they said the car was 25 miles an hour faster. Right? They said he was jogging at 25 miles an hour slower, meaning the car, the ride in the car was 25 faster. Right? So the rate in the car would be, the jogging rate plus 25. And then both the distances are the same, right? Because he's jogging to a friend's house and then going right back to the place he started from. So the friend's house is 12 miles away, so he jogged 12 miles and then got a ride the 12 miles back. Right, and then the times, right? The time jogging, 12 divided by J, right? Time is distance divided by rate. The time riding in the car, 12 divided by J plus 25. And then it said, you know, again, these times are not equal. They don't add to anything. What we hear here, it says it took him 2 hours longer to jog than to ride back. So the jog time, right? The jog time will be the ride time plus 2. Right? I hope that makes sense, right? The time it took him to jog to his friend's house is the same as the time it took him to ride back, but 2 hours more. Right? It should take longer to jog and then ride in a car. Right, so back again to the page, and I'll set up our equation. The jog time was 12 divided by j equals, or you could take jog time minus ride time is 2. If you want to write it that way, same thing. The ride time was 12 divided by j plus 25. And then we have plus 2. Right, so once again, LCD is just j times j, the quantity j plus 25. And then I'm multiplying every single term here by the LCD, canceling all the denominators. On the left side, we'd have 12 times the quantity j plus 25 equals, then the first term here would just be 12j plus, and then 2 times the LCDs. Nothing's canceling there. 2 times j plus 25. Alright, so over here we'd have 12j plus 300 equals, and then here we have 2j squared, and then 50j and 12j makes plus 62j. And then I would take away 12j, take away 300, and divide everything by 2. Alright, so bear with me here. Hopefully you understand where this comes from. So we'd have 1j squared. If I subtract 12j, that's 50j, divided by 2 would be 25j. And then subtracting 300 gives me minus 300, but then dividing by 2 gives me minus 150. Equals 0. And then this should be able to factor. So that's 3 times 50, 15 times 10, 25. Alright, so I'm going to think more about how to factor this, and I'll get back when I'm done. Okay, so as soon as I paused, I was like, oh, well, of course. Why didn't I see that a second ago? This would end up being j plus 30 times j minus 5, right? That'd be a plus 25j and then minus 150, right? Alright, and off to the side here, just so I don't have to bring in a new piece of paper. The possible solutions are negative 30 or positive 5. And as with all the previous problems, what makes sense? Well, if j were negative 30, that means he'd be jogging, negative 30 miles an hour. That makes no sense. There shouldn't be any negative speeds. This makes sense though. J equals 5. He jogged 5 miles an hour and got a ride back at 30 miles an hour. Right. So Matthew jogged 5 mph, right? 5 miles an hour here. Great. Okay, example 11. The next exercise. This would be exercise 295. So here we have Hudson travels 1,080 miles in a jet, and then 240 miles by car. So there are the two rows of our table, jet and car, to get to a business meeting. The jet goes 300 miles per hour faster than the rate of the car, and the car ride takes 1 hour longer than the jet. What is the speed of the car? So once again, keeping the problem up top there, exercise 295. This is example 11. Let's get our table in here, just like all these uniform motion problems. Okay. We have the jet travel. We have the car travel. And they want the speed of the car. So I'm going to call that C for car. Why not? Right? Let C equal the speed of the car. So this is the rate of the car. So this is going here. Right? C in the car row under the rate. Now they said the jet travels 300 miles per hour faster. So the jet's rate would be C plus 300. Alright, now the distances this time are not the same, so this problem's a little different than examples 10 and 9. It says he travels 1,080 miles in the jet. Right. And the car, he traveled 240 miles. And then the times, again, once two of these are filled in, you can fill in the other one. Time is distance divided by rate, so the time spent in the jet is 1,080 divided by C plus 300. The time spent in the car is 240 divided by C. Alright, and then one other key piece of information is that the car ride takes 1 hour longer than the jet ride. So time in car takes, right? Usually verbs will represent equal signs. The time in car takes, time in car is 1 hour longer than the time in the jet. So time in jet plus 1. Hopefully that makes sense. So time in car is 1 hour longer than the time in the jet. So time in the car, right, that's 240 divided by C. The time equals, right, takes the time in the jet plus 1. Time in the jet, 1,080 divided by C plus 300, and then plus 1. Same, now I'm solving this equation. Right, the LCD, C times C plus 300, and then I'm multiplying the one fraction on the left and both these terms on the right by the LCD. Right. On the left side, we have 240 times the quantity C plus 300 equals, and then the first term on the right side, you have 1080 C plus, and then just the LCD, C times C plus 300. Right, times 1, but there's really no need to write times 1. Alright, left side, distributing the 240 here, we have 240C plus 3 times 24 is 72. And you have 3 zeros, 72,000. And on the right side, distributing the C here, we'd have C squared, and then 300C plus 1080C, so plus 1380C. Okay. And then I'm going to take everything to the right and switch sides so that it's on the left. So I subtract 240C. Right, so we'll have C squared, and when I subtract 240C, it'll be 1140C, right, plus 1140, plus 240, 13, right, C, and I would subtract 72,000. And I'm going to kind of try to make sure, I'm going to try to get this on the same paper here. So let's drag this over here. I'm going to try factoring this polynomial. Alright, so I'm going to think about this for a second. I'll pause it for a second here and come back when it's ready. Alright, so I see now it would be C plus 1200 times C minus 60. And you can double check by foiling that you'd get this polynomial back. So the possible solutions here are negative 1200 for C or positive 60. And then once again, check, sure, both of these make the equation true, but, they don't make sense in the problem, some of them. Right, like the negative 1200, that would mean the car was going negative 1200 miles an hour and the jet was going negative 900 miles an hour, which makes no sense, right? You shouldn't have negative speed. So the only one of these that makes any sense at all in the context of the problem is 60. Right, the car would be going 60 miles per hour and the jet going 360 miles per hour. Right, so the car goes 60 miles per hour. Wonderful. Okay, next example. Example 12, which will be exercise 296. Alright, so here we have Nathan walked on an asphalt pathway for 12 miles. He walked the 12 miles back to his car on a gravel road through the forest. On the asphalt, he walked 2 miles per hour faster than on the gravel. The walk on the gravel took 1 hour longer than the walk on the asphalt. So we have this walk on the gravel and walk on the asphalt. How fast did Nathan walk on the gravel? There should be a question mark there, but alright, so let's pull this up. Example 12. Same thing every time, same beginning. I'm starting with this table, this chart for these uniform motion problems. Distance, rate, time. And then we have the walk on the gravel and we have the walk on the asphalt. And the question is, how fast did he walk on the gravel? I'm going to call that G for his speed, his walking speed on the gravel. So that's going to go in the rate for gravel, G. Now, it did say that he walked on the asphalt, he walked 2 miles per hour faster than on the gravel. So on the gravel he walked, G miles an hour, walked 2 miles an hour faster on the asphalt. So G plus 2. Nathan walked on the asphalt pathway for 12 miles. Distance 12 miles, that was the first sentence. And then he walked the 12 miles back on the gravel road. So another 12 miles back on the gravel road. So the time spent on the gravel was 12 divided by G. The time spent on the asphalt is 12 divided by G plus 2. And we are told that the walk on the gravel took 1 hour longer than the walk on the asphalt. So the time on the gravel, 12 divided by G, took, right? Usually verbs will be where the equal signs go. The walk on the gravel, right? The time on the gravel took or was 1 hour longer than the walk on the asphalt. So the time on the asphalt, 12 divided by G plus 2, and then plus 1, right? 1 hour longer. Hope again that makes sense. This is very similar to the previous 3 examples. So now LCD, right, is just G times G plus 2. And everything is getting multiplied by this LCD. Left side, the G's would cancel. Got 12 times G plus 2. Right side, first term, the G plus 2's would cancel. I'd have 12 times G plus, and then 1 times the LCD would just be the LCD, G times G plus 2. So left side, I have 12G plus 24. And the right side, I have G squared plus 14G. You have 12G here, 2G there. Alright, then I would take everything to the right and then we'll switch sides. So we'll have G squared and then plus 2g minus 24. And this is easily factorable. I don't have to pause the video this time. The numbers aren't huge. G plus 6 times g minus 4. Alright, so the possible solutions are negative 6 and positive 4. Alright, g equals negative 6 or g equals positive 4. And again, look at which one is the only one that makes any sense. If g were negative 6, that would mean on the gravel he was walking negative 6 miles per hour. And on the asphalt he'd be walking negative 4 miles an hour. Either way, you have a negative speed. You shouldn't be having negative speeds in these problems. So not going to use that one. The only one that makes any sense is g equals 4. Right? He's walking 4 miles an hour on the gravel, 6 miles an hour on the asphalt. But what they wanted was the gravel speed, right? So we have Nathan walked 4 miles an hour, 4 mph on the gravel. Okay, easy enough. Alright, so let's see if the next 4 are any different, right? It looks like they've been coming in groups of 4, how similar the problems are. So example 13, it's going to be exercise 297. So here, John can fly his airplane 2,800 miles with a wind speed of 50 miles per hour in the, so now we're back to like the first 4 questions with the wind speed, with the wind, against the wind, and they're doing the same. Okay, this is going to be very similar to examples 1 through 4. So with a wind speed of 50 miles per hour in the same time that he can travel 2,400 miles against the wind. So yeah, if the speed of the wind is 50 miles an hour, as it was stated, find the speed of his airplane. Alright, same setup. All right, example 13, exercise 297. So again, distance, rate, time chart. I'm doing it for all these uniform motion problems. We have traveling with the wind in the airplane, and we have traveling against the wind in the airplane. And I'm going to let A be the speed of the airplane. Right? This is without the wind. This is just the speed of the airplane, A for airplane. Right. Now remember, the wind speed is 50 miles an hour. So with the wind would be A plus 50. Right? You have the speed of the airplane plus the speed of the wind at your back. And then against the wind's rate would be the airplane speed minus 50. Right? You're slowed down by the wind. I hope that makes sense. Again, this is very similar to questions 1 through 4. Then the distance traveled with the wind was 2,800 miles. The distance traveled against the wind, 2,400 miles. So the time spent with the wind is 2,800 divided by A plus 50. The time spent against the wind, 2,400 divided by A minus 50. And we are told that these are the same. Right? It says in the same time. So the time traveling with the wind is the same as the time traveling against the wind. So we're just setting these times equal. Right? The time with the wind, 2,800 divided by A plus 50, should be equal to the time against the wind, 2,400 divided by A minus 50. Alright, now one thing I notice here is that this is just to make the numbers smaller and easier to deal with. 2,800 and 2,400 are both multiples of not only 100, but they're both multiples of 400. So I'm going to divide both sides by 400 right now. Alright, just to just to get the numbers to be smaller. So if I divide that by 400, it's going to be 7. So I have 7 divided by a plus 50 on the left. And dividing this side by 400, 400 goes into 2400 6 times. 6 over a minus 50. Right? And now the numbers are much easier to deal with. Alright, so same as always, the LCD is, again, very easy to see in all these problems so far. A plus 50 times a minus 50. And I'm going to multiply both sides by this LCD, and the denominators should cancel. Left side, I'd have 7 times the quantity a minus 50. Right side, I'd have 6 times the quantity a plus 50. Distributing, we have 7a minus 350 equals 6a plus 300. Subtracting 6a gives me a on the left, adding 350 gives me 650 on the right. So the only solution here is that a is 650. So remember that represents the speed of the airplane. So the airplane travels at 650 miles per hour. Again, please be sure to check these, back in the chart. Make sure it actually makes sense and that you have no negative speeds anywhere, and that the distance is equal to the rate times time for both trips, which it should here. Okay, great. So yeah, back to problems that are similar to the first 4. Right. And example 14 is looking very similar, but instead of against the wind and with the wind, we're against the current, against water. So this is example 14. This will be exercise 298. So it says Jim's speedboat, right, can travel 20 miles upstream, which means against the current, right, against a 3 mile per hour current, in the same amount of time, right? So we'll have time equals time upstream equals time downstream. In the same amount of time, it travels 22 miles downstream with a 3 mile per hour current speed. Find the speed of the boat, right? Just like the speed of the airplane in the last problem, right? What's the speed of the boat without the current? So, example 14. Yet again, that same chart. Making the same chart every time. So this time we're, with upstream and downstream. Against the current, with the current. And I'm going to let B be the speed of Jim's boat. B for boat. So upstream would be B, the rate of the boat would be B minus 3. Alright, they said the current was 3 miles an hour. And if you're going upstream, right, the current's slowing you down. So it's the speed of the boat minus the speed of the current. Going downstream, the current speeds you up, so it'll be B plus 3, right, plus the speed of the current. Traveled 20 miles upstream and 22 miles downstream. So the time spent upstream would be 20 divided by B minus 3. The time spent going downstream, 22 divided by B plus 3. And just like in the last question, it says that these trips are done in the same amount of time. So that's our equation. This time upstream will be equal to this time downstream. Let me write that out. So here's our equation. 20 over B minus 3, right, the time going upstream, is the same amount of time, is equal to the time going downstream, right, 22 divided by B plus 3. Alright, and then just like before, I'm noticing that these numerators here are both multiples of 2, so I'm going to divide by 2 first. That'll make this into 10 over b minus 3. And then 22 divided by 2 is 11. So you have 11 over b plus 3, right? Just to have some smaller numbers, that's all. Alright, now the LCD, alright, b minus 3 times b plus 3. I'm multiplying both sides by the LCD, and this will cancel all the denominators. The left side, we have 10 times the quantity b plus 3. The right side, we'd have 11 times the quantity b minus 3. Left side, after distributing the 10, we have 10b plus 30. Right side, after distributing the 11, we have 11b minus 33. And if I subtract 10b, I'll have b on one side, and then add 33, get 63 on the other. Right? So b equals 63. So yeah, so the speed of the boat, without the current, is 63 miles an hour. So the speed of the boat is 63 mph, right? 63 miles per hour. Great, and please double check that back in the thing, make sure it makes sense that all the distances are equal to their rates times their times. Okay, so that was example 14. Exercise 298. Now, next example, 15, will be exercise 299. So here, Hazel needs to get to her granddaughter's house by taking an airplane and a rental car. She travels 900 miles by plane and 250 miles by car. The plane travels 250 miles per hour faster than the car. Right. If she drives the rental car for 2 hours more than she rode the plane, find the speed of the car. Right. So, example 15. It's exercise 299 here. I'll pull up the paper. Same chart. The two trips, or the two types of travel here, are in the plane and in the rental car. I'll just say plane and car. And they want us to find the speed of the car. So I'll use C for car. Right? I'm going to let C represent the speed of the car. Right? So that'll go in the rate for the car. Now they do mention that the plane travels 250 miles per hour faster than the car. So the rate for the plane is C plus 250. The distance traveled by plane, it says she travels 900 miles by plane. It says she travels 250 miles by car. Alright, and now that I have this filled in, we can say the time spent in the plane would be distance divided by rate, right? 900 divided by C plus 250. The time spent in the car is 250 divided by C. And then the last sentence, before find the speed of the car, it says she drives the car for 2 hours more than she rode the plane. So the time in the car, 250 divided by C, is 2 more hours than the time in the plane. So the time in the plane, 900 over C plus 250, then plus 2. And I'll bring this up on make this bigger. So hopefully that makes sense, right? This is like earlier problems, right? The time in the car is the time in the plane, but 2 hours more than that, right? Plus 2. Alright, let me solve this. LCD simply just, C times the quantity C plus 250. And I'm multiplying everything on both sides by this LCD. Left side, we'd have 250 times the quantity C plus 250 equals, right side we have 900 times C plus, and then 2 times the LCD, nothing's canceling there. So 2 times C plus 250. Distributing the 250 over here, we have 250C plus 625, and then 62,500 equals, and then we have 2C squared over here, right? Then plus 500C plus 900C would be 1400C. Alright. Taking everything to the right, and I'll switch sides. We have 2C squared subtracting 250C plus 1150C. Right, 1400 minus 250 would be 1150. And then minus 62,500 equals 0. And then one thing I'm noticing here is that all the coefficients are even. So just to make the numbers a little smaller, I'm going to divide everything by 2. That gives me C squared plus 575 C minus, and then 31,250. Okay. And now I'm going to try to think about how to factor this, and I'll get back when I figure that out. Alright, so I figured out that this factors to C plus 625 times C minus 50. I'm bringing this over here. So the only possible solutions to this are C equals negative 625 or C equals positive 50. And then once again, like with every problem, you got to think about what makes sense in our chart, what makes sense in this problem. If C were negative 625, that means the car would be traveling negative 625 miles an hour. That makes no sense, right? You shouldn't have negative speeds. The only one that does make sense is C equals 50, right? The car is going 50 miles an hour, the plane going 300 miles an hour. So speed of the car, right, the speed of the car is 50 miles per hour. Wonderful. Okay, next example. Again, same setup with the tables. You just got to pay attention to how the equation is going to be written, which again, I know that's the hardest part every time. But with practice, you'll get used to it, I'm hoping. Alright, so next example, example 16. This is exercise 300. So Stu trained for 3 hours yesterday. He ran 14 miles and then biked 40 miles. So we have running and biking. His biking speed is 6 miles per hour faster than his running speed. And then what is his running speed? This example 16, exercise 300. And you guessed it, right? Uniform motion problem, distance, rate, time chart right here. Doing the same start every time. And we have running and biking. And they want to know his running speed. I'm going to let that be R. Right. I'll let it be lowercase r since I wrote a capital R up there for rates. So I have lowercase r be running speed. So I'll go here in the run row. And it does say his biking speed is 6 miles per hour faster than his running speed, so biking rate will be r plus 6. 14 miles he ran, biked 40 miles, right? So 40 miles for distance on the bike. The time spent running would then be 14 divided by r. The time spent biking would then be 40 divided by r plus 6. And now, right, the very first sentence said he trained for 3 hours running and biking. So the time running and the time biking together makes 3 hours. So I'm going to be adding these. So we have the time running, 14 divided by r, plus the time biking, 40 divided by r plus 6. This should be equal to 3 hours. Equal to 3. And I'll make this bigger and we'll solve this equation and check our solutions, see which ones make sense. LCD, simple enough, right? Again, it's just a very quick one, r times r plus 6. And I'm multiplying both sides, every single term, by this LCD, this r times r plus 6. On the left side, the first fraction, when I multiply by the LCD, would be 14 times the quantity r plus 6. Plus, then second fraction would just be 40 times r. And then the other side would just be 3 times the LCD. There's no denominators canceling. So 3 times r plus 6. Alright, distributing the 14 here and combining like terms, we'd have 54r on the left plus 84, 6 times 14, 60 plus 24 plus 84 equals on the right side, distributing the 3r, we have 3r squared plus 18r. Alright, then I'm just going to take everything to the right side here, and then I'll switch sides. So subtracting 54r give me negative 36r. So we have 3r squared minus 36r. Yeah, 36 and 18 make 54, right? And then subtracting 84, again, minus 84 equals 0. And then one thing I'm noticing is that all these coefficients here are multiples of 3. So I'm going to divide everything by 3. It's going to make the numbers smaller. We'll have r squared minus 12r minus 28. Yeah. 60 and 24, yeah. Equals 0. And this factors nicely to r minus 14 times r plus 2. Alright, so then bring this here, keep it on the same page. R could be 14 or negative 2. And once again, we're checking to see which ones actually make sense. Negative 2 does not make sense, right? Because again, you don't want negative speeds in these problems. Alright. So the only one that does is positive 14. So Stu here ran 14 miles an hour and biked 20 miles an hour, right, for these 14 miles and 40 miles. So that's what I'm going to write. Stu ran 14 miles per hour. Right? That's what R represented, his running speed. Okay. Next question. Example 17. This should be exercise 301. So when driving the 9-hour trip home, Sharon drove 390 miles on the interstate and 150 miles on country roads. Right, so we have interstate travel and country road travel. Her speed on the interstate was 15, miles per hour, more than on country roads. What was her speed on the country roads? Right, so again, I'll make my table. Right, this is example 17. Right? Yeah. Example 17, exercise 301. So again, distance, rate, time chart. And the two trips being discussed here are on the interstate and then on the country roads. And they want her speed on the country roads. So I'm going to let C for country roads be the speed on the country roads. So I'll go here under the rate for country roads. And it does say her speed on the interstate was 15 miles per hour more, so on the interstate the rate is C plus 15. It says Sharon drove 390 miles, the distance on the interstate, 390, and 150 miles on the country roads, 150 miles there. So the time she spent on the interstate would be 390 divided by C plus 15. And the time she spent on the country roads would be 150 divided by C. And at the very beginning of the question, it said the trip home was 9 hours long, right? When driving the 9-hour trip home. So the entire trip, right, the time on the interstate, along with the time on the country roads, makes a total of 9 hours. So adding these together should be equal to 9. So I have the time on the interstate, 390 divided by C plus 15, plus the time on the country roads, right, 150 divided by C should be equal to 9 hours. And then I'm going to make this a little bigger and we'll solve this equation. Alright, so LCD here, simple enough. And it's just C times C plus 15. And we're multiplying every term on both sides, every fraction by this LCD to cancel the denominators. First term, the C plus 15's cancel. Got 390 times C. Plus. Second fraction on the left, you have 150. The C's cancel, so then you have just C plus 15. It's 150 times C plus 15. Equals, and then the other side we got 9 times the LCD, 9 times C plus 15. Okay. Distributing the 150 here, combining like terms, we have 390C plus 150C, 540C. And then 15 times 15 is 225 with a 0, so plus 2,250 equals, and then distributing the 9C here, we got 9C squared plus, and then 90 and 45 make 135, right? So plus 135C. I'm going to take everything to the right. We'll switch sides. So I got 9C squared. Then 135, minus 540. That'd be 405, negative 405. So minus 405C and then minus 2250 equals 0. And then one thing I'm noticing here is that all these coefficients are divisible by 9. So I'm going to divide everything by 9 real quick. Get smaller numbers, so we'd have C squared minus 49C. 9 times 49 is 360. Nope, not 49. Not 49. 45. 45. Sorry. That should be 45C. So C squared minus 45C. And then dividing this by 9. 9 goes into 22 twice. 18 with 45, 290. Alright, because that'd be 1800. Oh, I did it again. 250. La. Yeah, because 9 times 25 would be 225 with a 0. Yeah, so 250. Alright, sorry about that. These should be 5s. So I have c squared minus 45c minus 250 equals 0. And yeah, this should factor nicely. This does factor nicely. This factors to c minus 50 times c plus 5 equals 0. Yeah. And then bringing this over here now. C is 50 or negative 5. Right, so C is either 50 or negative 5. And the only one that makes sense with the problem is 50. Right? Negative 5 doesn't work because you can't have we don't want negative speeds, negative rates. So it looks like Sharon's speed on the country roads was 50 miles an hour, and that's what I'm writing here. Sharon's speed on country roads was 50 miles per hour. Great. All right. So next example 18, just got a few more. This is exercise 302. So two sisters like to compete on their bike rides. Tamara can go 4 miles per hour faster than her sister, Samantha. If it takes Samantha 1 hour longer, and 1 hour is longer, 1 hour longer than Tamara to go 80 miles, how fast can Samantha ride her bike? So we have two trips here, two types of travel. Tamara is riding and Samantha's riding. Alright, so this is example 18. And I'm making the same kind of chart. Talking about distance, rate, and time. One for Tamara and one for Samantha. And the question is about Samantha's speed. How fast can she ride her bike? So I'm going to let S for Samantha, Samantha's speed on the bike. Samantha's speed, her rate. So that'll go under rate for Samantha. S. Said earlier, Tamara can go 4 miles per hour faster than her sister. So Tamara's speed will be Samantha's speed plus 4. Right, 4 miles per hour faster. And they both go 80 miles, it says, right? Because it takes Samantha 1 hour longer to go 80 miles than Tamara to go 80 miles. They both go this 80 miles. So the time it takes Tamara to go 80 miles is 80 divided by S plus 4. The time it takes Samantha to go 80 miles is 80 divided by S. And again it says it takes Samantha 1 hour longer than Tamara to go this 80 miles. So Samantha's time, right? Samantha's time, 80 divided by S, is going to be Tamara's time plus an hour. Right? It takes her an hour longer than Tamara. So it's Tamara's time, 80 divided by S plus 4, but then after that, plus 1, right? An hour longer. Alright, so making this larger, we'll solve the equation. So again, LCD, simple. LCD is S times S plus 4. We're multiplying everything on both sides by this LCD to cancel denominators. On the left side, I'd have 80 times the quantity, S plus 4, equals, first term on the right side, you just have 80S, plus, and then 1 times the LCD would just be the LCD, so S times S plus 4. Alright, so left side here we have 80S plus 320 equals, and over here we have s squared plus, and then 4s and 80s plus 84s. And then I would take away the 80s, take away the 320. We have s squared plus 4s minus 320 equals 0. And then, this hopefully is factorable. So I know it's got to have s in one, s in the other. Let's see, how about 32 and negative 10? No. 20 and 16, though. 20 and negative 16. Right? Plus 20 minus 16. That'll work. Yeah. And this equals 0. And so the only possible solutions here are negative 20. Right, negative 20 or positive 16. And as always, check them, make sure they make sense, right? The negative 20 doesn't make sense. It doesn't make sense for Samantha to be riding negative 20 miles an hour and Tamara to be riding negative 16 miles an hour. Right? You shouldn't have negative speed. So the only one that does make sense in the problem is 16. All right, so Samantha bikes 16 miles per hour. Excellent. And don't forget to check again, make sure things make sense. That distance does indeed equal rate times time for all these trips. All right, example 19. This is exercise 303, almost there. So here Dana enjoys taking her dog for a walk. Sometimes her dog gets away and she has to run after him. So we have walking and running. So Dana walked her dog for 7 miles. Wow, that's a long walk. Anyway, Dana walked her dog for 7 miles, but then had to run for 1 mile, spending a total time of 2.5 hours with her dog. Her running speed was 3 miles per hour faster than her walking speed. What was her walking speed? So again, same start, right? This is example 19. Distance, rate, time chart. And we have Dana running, we have Dana walking with her dog. And I'm going to let W be the walking speed, right? W for walking. So that's the rate for walking, W. And then it says she runs 3 miles an hour faster than she walks. So the running speed would be W plus 3. And it says she walked her dog for 7 miles, so that's the distance walking, and then had to run for 1 mile. So 1 mile under distance for running. So the time she spent running would be 1 divided by W plus 3. And the time she spent walking would be 7 divided by W. And then another key bit of information was that she spent a total time of 2.5 hours, 2.5 hours with her dog. So time running along with the time walking, the sum of these is 2.5. So we have the time running, 1 over W plus 3, plus the time walking, 7 over W, is equal to 2.5 hours. Now, me personally, I don't like, these are in fractions. I'm going to put this as a fraction. So 2.5, that's 5 halves. All right, so the LCD here is 2 times W plus 3. And we're multiplying everything on both sides by this. All right, so again, let's pull this up, make it bigger. So the LCD is 2 times W times W plus 3. So multiplying the 5 halves by that, and then the W, the 1 over W plus 3, the 7 over W, and multiplying all of those by the LCD. All right, so the first fraction on the left. The W plus 3's would cancel, leaving me with 1 times 2W. So I'd have 2W plus. Then the 7 over W. The W's would cancel, and I'd be left with 7 times 2 times W plus 3, or 14 times the quantity W plus 3. 7 times 2 times W plus 3. And on the right side, the 2's would cancel, and from the 5 halves, the 2's would cancel, and I'd be left with 5 times W plus 3. Okay. And then simplifying the sides, distributing the 14 here. 2W plus 14W is 16W plus, and then 14 times 3 is 42, right? 30 plus 12. And over here, distributing the 5W, we have 5W squared plus 15W. And then I'll subtract 16W, subtract 42, and I'm going to switch sides. Right? So we have 5W squared, and then 15W minus 16W would be minus W, and then minus 42. All right, this is equal to 0. And then again, I got to think about how to factor this. Now I know one of the factors would have to have 5W, and the other one would have to have W. Then I'd have minus 3 here, plus 14 there. There we go. Because that would give me minus 15W plus 14W for minus 1W, and then minus 42. Great. Alright, cool. And then the only solutions to this would be W equals negative 14/5, or W equals positive 3. And once again, the only one that makes any sense in the problem is the positive one. The other one doesn't make any sense because you can't have a negative walking speed. That doesn't make any sense. Alright, so W equals 3, and what did W represent? That was her walking speed, right? Dana walks 3 miles per hour. Or Dana walked, right? Past tense, 3 miles per hour. Right. Easy enough. Alright, now I have just one final example. And you notice how I start them all the same, right? Distance, rate, time chart. Just got to pay attention to the keywords, key information from the problem. Right, so the final example, example 20, this is exercise 304. So it's about Ken and Joe. Ken and Joe leave their apartment to go to a football game 45 miles away. Ken drives his car 30 miles per hour faster than Joe can ride his bike. And Ken is also apparently a jerk because he doesn't offer Joe a ride. Anyway, if it takes Joe 2 hours longer than Ken to get to the game, what is Joe's speed? Right, so back to making a chart. Right, this is the last example, 20 here. So I got distance, rate, time. And we're talking about Ken, right, who's in a car, and Joe, who is on a bike. We're asked to find Joe's speed. So I'm going to let J represent Joe's speed, Joe's rate on his bike. Put it in the rate for Joe. And it says Ken drives his car 30 miles per hour faster than Joe can ride his bike. So Joe plus 30. Right, J plus 30 is how fast Ken is going in his car. And they're both going to the same game from the same place, right? They're both leaving their apartment and going to a football game 45 miles away. So they are both traveling 45 miles. So both have a distance of 45. So the time Ken takes to get to the game would be 45 divided by J plus 30. The time it takes Joe to get to the game would be 45 divided by J. And at the very end, it says it takes Joe 2 hours longer than Ken to get to the game. So the time it takes Joe to get to the game, right, 45 divided by J, is the time it takes Ken to get to the game, but 2 hours longer, right, plus 2. Let me make that bigger. So again, I hope that makes sense. They're very similar to questions we've seen before, right? So the time it takes Joe to get to the game is, 2 hours longer than it takes Ken to get to the game. So you take Ken's time plus 2. All right, we're solving this equation, right? Once again, LCD is simple. It's just J times J plus 30. And we're multiplying everything by that LCD. Left side, we'd have 45 times the quantity, J plus 30, after the J's cancel. Equals, and the first term on the right side, the J plus 30s would cancel. I have 45J plus 2 times the LCD, 2 times J plus 30. Let's see, distributing the 45 over here, we have 45J plus, now 3 times 45 would be 120 plus 15, 135, 1350, right? Yeah, to 0. So 1350 equals, and then distributing the 2J here, you'd have 2J squared, and then 60J plus 45J would be 105J. Alright, then again, I'll take away 45J, take away 1350, and then I'll switch sides so that everything's on the left. So we have 2J squared. After subtracting 45J, there'd be 60J, right, plus 60J. And then subtract 1350. Alright, equals 0. And one thing I'm noticing here is that all these coefficients are even, so I'm going to make the numbers smaller. Divide everything by 2, so we have J squared plus 30J minus 675. Yeah, 675, right? Yeah, 1200 plus 150. Yep. And then I'm going to try factoring this. So I know that I'll just do this over here. So I know one factor is going to have a J, the other factor is going to have a J. We're going to have a minus and a plus, right? I'm looking for factors of negative 675 that add up to 30. Let's see, you know what? I'm just going to think about this and come back when I have them. Maybe you see it already, but I don't just yet, sorry. Alright, so those factors are positive 45 and negative 15. So this factors to J minus 15 times J plus 45. So the possible solutions are J equals positive 15 or J equals negative 45. And once again, the negative one doesn't make sense for the problem. Right, because if you can't, Joe can't be riding his bike at negative 45 miles an hour. That doesn't make any sense. You shouldn't have negative speeds. Right, so the only one that does make any sense here is 15. So Joe is riding his bike at 15 miles an hour, whereas Ken's driving his car at 45 miles an hour. Right, but they wanted Joe's biking speed. Right, so Joe is biking at 15 miles per hour. And that's the answer to our question. Fantastic. Alright, so I am hoping that watching me go through these 20 examples of uniform motion problems, right? Distance, rate, time problems, distance, speed, time problems. I'm hoping watching me go through these 20 examples, or however many examples you did watch, help you out when you're working on similar stuff. And thank you very much for watching.